We're gonna pause this. Everybody listen for the tone that indicates caution. All right, so we're gonna talk more about bombs, and we're gonna talk about making and breaking bombs today, okay? So who can tell me what you need to do to break bombs? What do you need to do, Gabe? Do you know? Well, heat is a form of what? Okay.
Energy.
You need energy to break bombs. Okay. Any kind of bomb. What if I have a bunch of water molecules all chilling out? Chilling. They're chilling out as ice. That's what ice is. So ice is frozen water molecules. I'm feeling a little bit like I failed you hard that you don't know that. So we've got a bunch of frozen water molecules chilling out as ice. What do I have into it? Ooh, we have caustic.
Magma, fire, volcano,
Energy.
Fire, volcano.
Okay, so we have magma, we have fire, we have volcano. I did not hear lightning. Lightning?
Energy.
Energy. I need to put in energy to break these bombs. That one evaporated. That one had so much energy, it flew right off. That one evaporated. Okay. You put energy in, and the bonds get broken. Can I put more energy in to break these bonds?
Yes.
But it'll be significantly more energy, right?
No.
Am I going to do that right now?
Yes.
No, because it would destroy my little water molecules, and I worked hard to make those. So I'm not going to put in the energy to break apart my water molecule today. But does that happen?
Yeah.
Do water molecules get broken apart?
Yeah.
They do. Yes, Gabe.
The amount of energy you put in.
But it didn't. Clearly, this water molecule survived. Jaden.
If something is solid, is it frozen?
Yes, if something is solid, it's frozen. So I've got a frozen table. I've got a frozen pen.
I'm frozen.
I have a
I'm
frozen
frozen.
Me and my dad had like a debate on if something's solid, it's frozen, and he said it has to be ice frozen. I'm gonna tell him that if it's solid, it's frozen.
So the
You
only
could
solid in the
totally.
world.
I mean, have you guys ever melted plastic?
Yes.
I mean, it happens, right? If I stuck this pen on the stove and I turned the stove on and I put energy into the pen. Thank you, Gabe, for my clarification. If I put energy into the marker, then the bonds would break, right? The bonds that make this pen shaped and that make the plastic part would break. And I would no longer have hard plastic. I would have liquid plastic, which is not. Can you evaporate marker plastic?
Yeah.
Yeah. Have you ever put a pen on your stove and had it, or something plastic on your stove and smelled it?
No.
Yes.
Or like, if you never had like a scraper or like a plastic spoon fall down in your dishwasher and the dishwasher's going and the heating element turns on and you're like, what's that smell? Have you guys had this happen?
Yeah.
Oh, you guys have such a better life than I have. I've totally had that. And you're smelling like my house, it stinks. What stinks? The dishwasher stinks, and you open it up and there's this melted. Well, guess what happened to those plastic molecules?
They melted.
They melted, but then they got so much energy, they evaporated, and you've got nasty plastic molecules in the atmosphere that you just breathed in and you smelled, and that's how you knew that your plastic spoon was melting in the bottom of the dishwasher. Those of you who have not had that chance to smell that smell,
Don't ever do it.
it's a bad smell. And I can't help but think that it's not healthy, that it's like a bad thing to be smelling melted plastic. Like that can't be good for your body. But
It's not.
But luckily your body is like, whoa, let us not smell the smell. Open a window, let's get it out of here. Nobody's gonna sit there melting plastic on purpose to smell it. Nobody's gonna do that. 'Cause it's
Well, maybe
horrible.
now they will.
No, because they might be curious. I'm gonna melt this food, and then they're gonna go, oh, Mrs. Barlow was wise, and she knew things. That this is horrible. So if it causes cancer, nobody's hanging around with melted plastic all day, except for the people at the plastic company and their life
Yeah.
staff. So, but anyway, it took energy to break these bonds. Now, what is released when we form bonds? Heat. Heat is what?
Energy.
Energy is released
Automatic translation.
when we form bonds. Now, I am having to put in energy to form these bonds by hand. In real life, when these bonds are formed, energy, I lost my,
It
You
it
threw it on the
evaporated,
floor.
but it came back and deposited again. Okay, so energy is released when bonds are formed, okay? So, when we have ourselves a chemical reaction, let's take one of our favorites. What's this the reaction of? What's CH4? Do you guys remember what CH4 is?
Is it methane?
It's methane. It's one of our favorites because it burns and it doesn't have 1,000 molecules about it.
It makes water.
So remember, like wax was like what, like C13H?
Yeah.
No, it was like
56.
H64.
It was huge. It was, yeah, it was like C31, H64. CH4 is great. And methane, I mean, it's just Calvert. It is. Methane is Calvert. Calvert makes methane. Okay, so CH4 is a greenhouse gas. That means that it traps heat in. Do you know what is the most potent of all the greenhouse gases? No, not CO2. What's the most potent of all the greenhouse gases, Jaden? Nuclear bombs are not a greenhouse gas. What is the most potent? It traps heat better than any other chemical. Chad's eyes are squinty. Does Chad know? Guess, Chad, guess.
CH4 or O2? Sulfuric acid.
What chemical have we learned absorbs heat out of things extremely well?
Water.
It also retains that heat really well.
Water.
So when you burn methane, you actually get two greenhouse gases out of it. You get H2O plus CO2. Should we balance this real quick? Let's balance it. 'Cause we're gonna-
That's causing
You need
greenhouse
two
effect.
CH.
It doesn't. Okay, but you know that we die without some greenhouse effect, right? Like we freeze to death. So, I mean, it's not all bad. So we have 4 hydrogens and only 2 hydrogens. So let's give ourselves 2 more
You need
hydrogens.
two oxygen.
We have 2 oxygens and 4 oxygens.
You need two
So I
oxygen.
need to double the oxygens, and I think we're balanced now, right? Because the carbon and the
It
carbon.
looks like 20 to the 2.
Yeah. I mean, so that's balanced. So does this molecule get broken?
Yeah.
Yes, because that C joins up with the O2 and the H joins up with the Y. I mean, this one gets broken. So we put energy in. Energy. We put energy into breaking it. Does this one get broken?
No.
We're gonna say it does.
Oh.
We're gonna do energy in.
It says bonded with
Okay.
itself and then it breaks apart.
Yeah, and then does energy come out because we made a new thing?
Yeah.
It's called thermodynamics, and then energy comes out.
Energy.
Okay. So here's a question. In this particular reaction, does more energy come in or does more energy come out?
Equal.
You're saying it's equal. What does this,
More energy.
what did literally half of you say was the product of burning methane and oxygen? No, literally half of you said was the product of burning wax.
Oh, yeah, energy.
Fire.
Which is higher.
We also get energy out. So do we put more energy in or do we get more energy out? Out. I'm going to draw these arrows huge because we get more energy out.
Just weird.
Little bit of energy in. big energy.
Which is weird.
It produced energy. People burn methane for the energy. They don't burn it. They don't say to themselves, there is not enough water in this world. I'm going to burn myself some methane to get some water. No, they never say, I don't have enough CO2. I'm going to burn methane to get CO2. So they burn methane to get fire.
So if I have like.
I love that fire. They're just like.
If you have a planet with a methane atmosphere and no water, your burn smells thinking better because you have some oxygen burn. Yeah, methane and oxygen, light yourself a match and get yourself some water.
Okay,
And after you completely burn the planet to bits and it's all dead, but you'll have water. Okay, Jaden.
Wait, so could you turn the water and carbon dioxide back into the CH4 and then the O2? And that would take less energy, and then it's just an energy duplication loop.
Is this a reversible reaction?
Oh,
No, it's really not.
Oh, I wanted to do real life duplication.
What happens is, this is what happens.
Really?
Energy. A snake.
A dinosaur.
Yeah.
A
dinosaur. Mrs. Barlow drew something recognizable.
That's a really
It
good
looks like
dinosaur.
that
Sinclair.
Yeah, that.
That's
Yeah,
actually
No.
a really good dinosaur, Mrs. Barlow.
it's the dinosaur.
I'm kind of proud of myself. So this guy
It's a dinosaur.
ate a bunch of plants.
Ooh.
And
Yes,
then
yeah.
one day,
He
now what are the
no
plants
longer
made
had
of?
an eye.
He has
What
an
are the
eye
plants
patch.
made of, guys?
Plant.
Carbon. Carbon, nitrogen, and hydrogen. So this guy died, and we're gonna pretend he fell over.
And then we burn it.
I have 0 disease. And then he buried, and his body turned into oil. And we get methane from the oil. We also get methane from.
We're burning the
We
dinosaur.
turn it into gas. That's not really how we get methane. Methane is actually produced cows burp. So the cows eat the grass and they turn it into methane and they burp it out.
So people just go get burp.
If you put a plastic bag over your cow's face,
And then it dies.
it'll die. So, and actually, if you give a plastic bag to a cow, the cow will just eat the plastic bag and get sick. So don't do that. But anyway, it comes from, it started as grass. So
So we
yeah,
burn
methane
the
started
dinosaur.
as grass. And the oil, the gas in your car started as grass. And then the dinosaurs.
Wait, the
ate
grass in the car.
Burning the dinosaur.
My
Yeah,
cars
that's
are
why
not
it's called
dinosaurs.
Guys, that's why it's called a fossil fuel. Because it started as a fossil.
My
So,
cars run on dinosaurs.
let's look. I want to show you guys a couple of exothermic reactions that I can't duplicate here because you'll see.
Run on dead cow.
Okay, go away, menu. All right, you ready? Hey, you guys are super chatty over there. I'm going to separate you in a second.
Is this the boring lady talking? Is she gonna talk?
Okay, so that's the burning of thermites. Was energy released in that reaction?
Yeah.
Was more energy
Not at
released
all.
than went in?
Maybe a little bit.
Okay, let's go try another one. We didn't get the boring lady. She just didn't even talk. She fell asleep because she put herself to sleep.
Oh, thermite.
That's what the last one is. What just happened?
With a feather and it explodes.
Like if you tickle someone with a feather, they start laughing.
So these are reactions we don't do at school. All right, did more energy go into that reaction or did more energy come out of that reaction? Out. Okay, so there are words for this. If more energy comes out of a reaction, like burning methane and exploding the thermite and all those things is called exothermic. So let's look at this
Endothermic.
word. We've got a prefix and we've got a suffix. We've got exo and we have thermic. This one's easy. What does thermic mean?
Heat.
Heat. Thermic means heat.
Oh, hi.
It's breakfast grandma. So thermic means heat. What does exo mean? What do you-
Outside.
How do you know?
It's exoskeleton.
Yeah, that's.
Oh, because exoskeleton is a skeleton on the outside of your body.
Is there
What
also
door do you
endothermic?
leave to leave a building?
The exit.
The exit. So
The
in an exo
entrance.
leave. In an
Mhm.
exothermic reaction, energy leaves. What is that energy usually in the form of?
Heat.
Heat. What about our glow sticks last week? What energy was that in the form of?
Light.
Light. Okay. So you have heat, you have light, energy leaves. Do we ever have reactions where energy enters?
Yes.
What would we call that? Great.
Endothermic.
Oh my gosh, she knew that! Endothermic. Kind of like enter.
Entrance.
Entrance, means enter. And then thermic.
Endo.
Where you're turning those back to
Where you're what?
turning water into back.
Yeah, if we were able to do this backwards,
Then
it would be an endothermic. Should we play with some endo and exothermic reactions?
Yeah.
Let's start with an endothermic reaction. So I have this little,
chicken.
What is it?
it's called a whack-a-pack balloon.
It's a
Oh,
chicken.
And you whack it.
Whack it.
I was expecting it to like blow
up or something.
And it blows up. Woo, feel it. Pass it around and feel it.
That's kind of
What?
Ow, I heard that one. Pass it around and feel it.
weird.
Okay, how does it feel?
I don't
I want to explode it.
How does it feel?
Like really
Like a brain.
tight.
What temperature does it feel like?
Warmer.
Free, what? Feel it.
It's supposed to be cold.
Oh.
Yeah, but ours isn't cold.
Yours is too cold. I felt it.
It blows up.
If you feel like right there, it's cold right there.
Okay.
Feel the side, guys. It feels
Oh,
cold.
you popped ours. Yeah, it ours though.
Oh, yours is like leaking. Does it feel hot or cold though? Kenny, do you feel it? Does it feel hot or cold? It's room temperature in some places, and in one little spot where the chemical reaction is happening, it's cold. So that they reacted some things that let me tell you the reaction. The reaction on the balloon is, I think, it's citric acid and baking soda. Is all that is. Okay. So the citric acid and baking soda. I'm gonna write this. So the citric acid and baking soda. I don't have the formulas here. We have the acid and we have the base. And it produces CO2 and water. So does more energy go into breaking these bonds or forming these bonds?
Forming.
Breaking.
Breaking.
More energy went in. It is, if you touch it and you feel the cold, it's pulling energy out of your hand. So big energy goes in.
Waste of energy.
Little energy comes out.
See the surprise.
Okay, so Gabe says it's a waste of energy.
Yeah, I think it's
But you got a cool poofy balloon out of it.
I think you're supposed to break up in the package,
You're not supposed to break open the pack.
but it says to.
So you're supposed to just pop.
It says poof.
You should pop it.
Yeah, you,
And
you,
then it says,
you
"See
smack the
surprise."
packet and you watch and you wait. And that's what I did. Yes, Chad.
I think what you did for this one, you just pop the inside part that has the chemicals in it, you pop the outside part.
All right, did you want to smack it again?
Hey, it's the first thing.
Hey, Jaden,
Smash
Do
it.
you have an endothermic fire?
There, whoa.
can you have an endothermic fire? In science fiction movies, they do that quite often, but I haven't heard of one in real life.
No.
Wow, that was exciting. And we had science happen. Like on Doctor Who, there was a sun that burned cold and it sucked the heat out of you. But that would have been a nuclear reaction. So I don't know. But not in real life. In real life, you do have cooling reactions. So like that's how air conditioners work, but they're not fire. All right. So now we're going to do an exothermic reaction. Now these hand warmers, guys.
All I think of those, when I think of those, all I think of is one thing.
How many of you have ever used these before?
I use
So they're
I've
in
used
a
the
plastic
table.
container so that they don't get in contact with air. They contain iron filings and they contain carbon, graphite, and then there's little holes in the packets to let the oxygen come in. So I shake it, and I hope, because they're a little bit old, and these are plastic containers, so the oxygen can't get in. But we do know that oxygen still gets in, so they might be.
They take forever to.
They take forever, but then they last a long time, right?
But see, the purpose of that is so that you shake them and warm up your hands just by shaking them.
Okay. They're getting warm. Pass and
See,
enjoy.
look, there's
Your
a hole.
laptop matches your jacket.
What?
Look, it's like the same. Oh,
No,
your laptop, from my point of view, is reflecting the color of your jacket.
Oh,
Okay.
sad.
I didn't get frostbite.
So these are the reason that he didn't get frostbite. So on this one, the reaction is between iron and oxygen.
You have one now, Bree?
So we have iron and we have oxygen, and that is reacting to make ferric oxide. We have iron and we have rust. You can eat rust and not die, and I hope you eat iron because iron is good for you. Maybe don't like chew on nails, but I mean, chewing on nails would actually not hurt you. If you swallowed a nail, the poking
It would
of the
hurt
nail
you.
would hurt you. But if you just swallow, like if you chew on a nail, like cooking in a cast iron pot, and some of the iron leaches into your food, yay, you get more iron. And you need iron to make red blood cells. So there's that.
Iron over.
If you can overdose on iron and it is toxic, you wouldn't be able to do that from eating on the pot. You can do that from taking iron supplements. Like if you have multivitamins with iron in them, you take too many of them, they would kill you. I actually take a specific iron supplement that's just iron. And number one, it has to be liquid so I can digest it. And it's so nasty, but it's in a childproof cap so kids don't just chug it because it would be toxic. But anyway, for a moment. So does it take, now this is not bonded. I mean, it's kind of bonded. It's bonded with its other ions, right? So we're still breaking this apart from its other ions, and we're breaking this apart. Does it take more energy to break these bonds or to make these bonds?
More energy to break them.
Break them.
Make
Make them.
Oh, yeah, that.
Because the energy is leaving. More energy is leaving than is going in. So it takes more energy to break the bonds than to make the bonds, okay? If it's exothermic, it takes more energy to make them than to break them, because when you make them, it's released, and you get that energy out. If it's endothermic, it takes more energy to break them than it takes to make them, okay? I think there are far more exothermic reactions that you guys are familiar with than endothermic. Anything involving the combustion of anything is an exothermic reaction. So anything burns and you get that nice heat off of it, that's an exothermic reaction. And it takes a very, very, very little bit of energy to break those bonds, and then you get a huge amount of energy released. Huge amounts of energy are released. Okay, so you guys are gonna play today with some endothermic and exothermic reactions. You're gonna combine things in little cups. A lot of things are pre-measured for you today. Be aware of that. They're over there on the side table so that you don't have to measure them yourselves, okay? All right, any questions on this stuff? Gabe?
Would cesium and water be exothermic?
I don't know, actually. Oh, cesium and water? Oh, yes. All of the alkali metals, all the alkali metals and water, those are all exothermic reactions. I'm like, I don't know. And then I looked at the periodic table. Oh, I do know. Yes, I do know. Cesium and water is very, 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 it's exothermic enough like it would blow a hole in the world.
It's like
Blow a
I
hole in
saw
the
it
world.
and they put it in a fishbowl and it like cracked from the safety glass.
Oh, I've seen a video with cesium and they put it in a lake and it blew up the lake.
Why would you do that?
That's right.
So it doesn't blow up the world.
The question I think more, Gabe, is
Let's go put it in ground.
if you could make a giant explosion by dropping cesium in a lake, why wouldn't you?
Because it would cause widespread damage.
No, you go to a lake that's not populated. Yes, Jaden.
If you use like a bunch of cesium in Yellowstone and like blew up all the geysers, the volcano explodes because the pressure wouldn't be escaping.
Okay, so there isn't enough pressure down there for it to escape right now anyway. What makes the volcano explode is the pressure of the lava, not the pressure of the heat.
Right, isn't it the more liquid it is, the more
It's like geysers and
Not necessarily. Depends on what kind of volcano it is.
liquid.
But we're really not anywhere close to the Yellowstone volcano erupting right
If it were
now.
to happen, we'd have like decades of
Yeah, we would.
If it were to happen, we would have like
yeah.
20 seconds to run.
Oh, we'd have more. We'd have a couple hours.
Really?
We wouldn't be able to outrun it. We'd have enough time to know we were going to die.
Really? Because in 5th grade, they freaked us out
Yeah.
hard with that.
They're like, you have 10 seconds until all the lava comes down and kills you.
Okay, so you want to do the math on that?
Sure.
Like we could squirrel a little second here. So the pyroclastic
They were like, we don't know when it's gonna
flow
blow
from a
up, and when it does,
volcano-
we're all gonna die.
The pyroclastic flow from a volcano goes at about, what was it, Chad? Was it like 80, 90 miles an hour, the pyroclastic flow, or is it a couple hundred? I'm having a brain fart. We're gonna pause and Google here. Okay, so the second grade teacher out there is like highly entertaining, by the way.
Yeah, I just like.
Did you guys see that? I look out there and there's something exciting. Speed of pyroclastic flow. We might have to do this later.
200 meters.
200 meters per second. Okay, we're gonna do this later because we really do have stuff we need to talk about. We're gonna do the math later, but we're gonna write that down. It goes at about 200 meters per second. Okay,
That's pretty fast.
so let's go back to Zoom. Are you guys, we're gonna completely 100%. I really like to lump things together so that you're doing kind of the same thing every day. In order to do that, I would have had to have you guys do 4 lessons a day one week last week, and I didn't want to do that. So we are going to completely switch gears. Are you guys ready to completely switch gears?
Yes.
Okay. Are you ready for a magic trick?
Yes.
Yeah, totally.
So we know all the math.
You don't know all the magic tricks.
I know.
Go ahead and put it up because I'm going to hold it up so you guys can see. I have here a green liquid. Why is it green?
Because it's green.
Because green is my favorite color. I am going to, now what school did I go to for college?
A college. A college state university.
I did not go to Utah State. I went to the University of
ISU.
Utah. What are the colors for the University of Utah?
Green.
Red.
Red and black. I mean, like, guys, come on. So,
Is that
do you not see my Utah Utes lanyard with the red and the red and the red? Okay, I am going to turn to my favorite color.
Indirect.
Into red! Go Utes!
I was right. This is Barlow. I know a college.
Now, here's the deal though. Before I went to the University of Utah, I went to Snow College.
No.
Cute little 2-year college in central Utah. My son goes there right now. What's Snow College's color?
I
Oh!
know.
Blue! And what's ISTCS's color?
Blue.
So my favorite color is green. I went to the University of Utah. But blue's important too.
What if I'm a
Purple! And then if I keep going, oh, this one's purple, which is actually my second favorite color.
I know.
It
a
got a
college,
little
but-
excited and it got a little more blue than I intended it to. And it's purple. What in the world? What?
It's universal indicator solution.
Jaden, what is it?
You turn food coloring into a powder.
I did not turn food coloring into a powder. No food coloring was used in the demonstration of this demonstration.
In the demonstration of this demonstration.
Did a chemical reaction happen?
Yeah.
How do we know that a chemical reaction happened?
Color
Does it
change.
change color?
Because it changed color. If it changes color, then there was a chemical Did I have chemicals hiding in these cups?
Yeah.
Totally, I
It
have
wasn't
chemicals
really
hiding
hiding,
in these
but-
cups because I do that and I do that and that's what I do.
What if you mix them?
What if I mix them? Should we do it?
Yeah.
Do it.
They turn back to green.
It's a
Don't
llama.
sue me if it blows up the school.
Okay, nothing. Nothing.
Well, it's more red.
Whoa.
What
It went
the?
orange.
That's how colors work.
Red plus blue
There
equals
wasn't enough to make
orange.
it green.
Yeah.
Oh, wait.
Now add the green.
Now I'm gonna do
Add
it.
green.
The green won't, they won't change the color.
Aw.
But.
Just add it.
Uh-oh, you're.
Oh no.
I could
Hopefully
sure
everyone will
have
do it though.
make it green if I tried hard enough.
But we want our school.
We got this.
Alright, so I have more purple.
We got this.
Easy enough to make more purple. Woohoo! Right? And I have
Ready?
now this kind of an orangey color.
It looks like so.
Oh, it's fizzy.
It looks like
bubbly.
It's orange wine.
It's orange with fizz.
It's orange
Is
soda.
that another evidence of a chemical reaction that I have?
It
Yes.
kind of
I
looks
do.
more like cream soda.
It does. It looks like cream soda. Am I going to drink this?
No.
That would be poor life choices.
More like.
Oh!
That's
Yes.
okay. So we're closer to green. We're kind of a yellowy yellow color.
Yeah.
Yeah.
Yeah, we did pretty good then.
Why
Then we
would-
were back to green.
Question. Why would it get darker and then get lighter?
Why would it get darker and then get lighter? What do you guys think? What do you think, Juden?
That's your answer to everything.
Did it reverse the chemical reaction? No. Well, actually, yes. A little bit.
One of them was more. acidic.
Okay, let's think about what happens. Breathe. Does anybody else have any ideas before I answer this?
It's more acidic.
More acidic. Well, that was more basic. Okay, let's think about it. Okay, so I've got this cup here, right? And it's filled with a liquid. When I first pour it in, it's really concentrated right there. And then I swirl it around and it gets mixed up. So when it first is really dark, that's super concentrated right there. I swirl it and it gets mixed up. So
Then it gives
what in the world? My awesome. What's happening here, people?
right off.
A chemical reaction.
A chemical reaction is happening. Between what and what and what and what?
Universal.
Brooklyn, what's in the green tab?
Universal indicator solution.
Universal indicator solution.
Yes.
UIS.
What does universal indicator solution indicate universally?
pH.
It indicates pH.
Not
So
pH.
it will tell you if something needs to start with the sound, right?
Like phosphorus.
Like phosphorus and
Physical.
phalanges and phalanges. Are you guys believing me?
No.
That's good because I'm so full solution because it works for both acids and bases.
Yeah.
Some indicators only work for acids and some indicators only work for bases. What the heck am I talking about? So I want you guys to look. So pH this H is important. Jacob.
Wait, is it a salt, the powder thing you use? Is it a type of salt?
So I use two powders. I use citric acid
Powder.
and I use sodium carbonate.
Like the balloon.
Yeah.
Never
In
mind.
fact, if I feel this, not super cold.
Oh, is that you're putting
Okay, I
sodium?
use citric acid and sodium carbonate. Okay, so let's look at this H though. What do any of you know what pH means? What it means in English, and we need what it means in English and what it means chemically. So what does it mean in English? Brooklyn, I think you know. What does pH
How
measure?
acidic or basic something is?
Okay, pH measures how acidic or basic something is. Okay, is that what you're going to say, Gabe? But she needs a turn to talk to. Good, all good. So it measures how acidic or basic something is. But what makes something an acid?
Nope.
Not the fact that it melts your skin. In fact, bases are often more dangerous than acids. If you gave me the choice of drinking a strong acid like lemon juice versus a strong base like lye, the lye is going to send me to the hospital with permanent damage. The lemon juice is going to taste bad. So actually, technically, lemon juice isn't that strong of an acid, but even hydrochloric acid, I've got hydrochloric acid in my stomach.
We'll be like, yay.
Hydrofluoric acid, I'm not drinking that. But hydrochloric, I mean, I have it in my stomach. You make it. You all make it. And so our bodies are designed to adapt to acids, and that doesn't mean that acids are not dangerous. But bases are often more dangerous. People are like, ooh, acid, but bases need to be respected, guys. Okay? So what makes an acid an acid?
Oh, lemon.
It's acidity. Thank you.
I'm
Dave.
ready.
This guy right there, the H makes it an acid. pH is a measurement of the number of the concentration of H plus ions that are floating around in a solution. Okay? Acids have H pluses that break off and they get in the solution. So we have a bunch of H pluses. Now, in your reading, you're going to read about H3O plus, okay? H3O plus. Sometimes the H pluses are just out there on their own, and sometimes they join forces with an H2O and become an H3O plus. It's the same thing, okay? Yes, Gabe.
So an H minus would be basic.
No, an H minus is not basic, but I love that you introduced us to this. H plus is acid. OH minus is basic.
Whoa.
Negative.
Oh.
Oh.
If I have a bunch of OH minuses floating around in a solution.
Okay.
Oh.
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 You have to be negative.
Oh.
Oh. Oh.
What is this?
Oh.
What is OH minus? It's going to be basic.
Oh, I thought you were asking.
Okay. So these are acids
Oh.
and these are bases. Now I chose my colors carefully. What colors are acids with universal indicator solutions?
Red.
Yellow, red, orange. What color are the bases with universal
Green, blue, purple.
Blue and purple. What color is it when it's neutral?
Green.
Green. Because it's our favorite color. I didn't even think about acids and bases when I put on a green shirt this morning.
Wait, like the bottom of it is red. The green.
Oh, the bottom of it is red. Oh, that is so cool. We've got some acid hanging out in the bottom.
Shake it.
No, I'm not going to stir because I want you guys to. You see it? You see it.
It's really cool.
Oh, and you guys can see it big on the screen.
Whoa.
So cool. Thank you for noticing that, Brooklyn. All right, so let's talk about the pH scale. When you get to Algebra 2, you will learn about logarithmic scales, okay? And you will learn about logarithms. Logarithmic scales, they go up by a power of 10. The pH scale is a little bit backwards than how you think it should be. It measures the acidity of a solution or the basicity, okay? And it goes from 1 to 14.
Yeah.
It goes by the power of 10.
And they go by power of 10. So, but they go the far, okay, so neutral is 7. This is acid. This is base, okay? Something that has an acidity of 1 is 10 times more acidic than something with an acidity of 2, with a pH of 2. Something with a pH of 2 is 10 times more acidic than something with a pH of 3. Coca-Cola syrup and lemon juice are both in the 2 range. So,
So that's why.
okay. So the farther away you get from 7, 7 is neutral, okay? So the farther away you get from 7, here's our little chart here. 7 is right there, neutral. The more you go this way, the smaller the number, the more acidic it is. Now, I don't like this chart because it shows a 0. You cannot physically, mathematically get to 0. You can get to point 0, 0, 0, 0, 0, 0, 1, but not 0, okay?
You should just take a Sharpie.
You can get to 14. Okay.
Everyone.
So
Why does it say alkaline instead of basic?
alkaline and basic are synonymous.
No, choose a time.
So the alkaline earth metals, guys, what do you think that they produce?
Oh, wait.
They produce bases. Mhm. So alkaline and basic mean the same thing. We'll be calling it basic. If you toss out an alkaline, I'm not gonna. I'll be like, woo, they remembered and look at them. But it's not anything that's gonna be like on a test or anything. Okay.
So you're wrong.
So you guys are going to play with with acids and bases and to see the concentrations. And if you put more drops in, does it become more acidic? If you put fewer drops in, is it less acidic? What do you think? If I have, let's say I have a drop. Okay, I'm going to erase this up here.
What if I have liquid H?
If you have liquid H+, it's called an acid, and this is what we have.
Whoa.
So, I mean, most acids come along with other things. Let's say I have a drop, and this drop has, it's a very big drop with very few things in it. And this one drop has 3 H pluses in it. So I put it in, and now I have 3 H pluses.
Well, that expands a lot.
I'm putting it in some water, okay? And then I put in another drop.
Oh, okay.
Okay, I'm putting in another drop. So now how many H pluses am I going to have?
6.
6. Is it more acidic or less acidic?
More.
More.
Why would it be less?
I don't know.
You have more H pluses, so it's more acidic.
Okay.
But it depends on the concentration too. So actually, if you're just combining volumes, the concentration isn't going to get that much. But yeah, we're adding H pluses to that volume. So now it's more acidic. Okay. What if I add another drop?
It's gonna be more.
It's going to be more acidic. We're making all the acids.
What if I added an H plus, like an H plus?
Okay, let's talk about what the H plus is.
Hydrogen with the next, with the less.
It's a hydrogen that's missing an electron.
Yeah.
Can it get any more positive than it is?
No.
I was thinking the other.
Because remember, how many protons does hydrogen have?
1.
1. And sometimes it has a neutron and sometimes it doesn't. It usually doesn't. So hydrogen usually has, and then it has one little electron. This hydrogen's electron. So an
No, get
H
rid of
plus is
No,
a hydrogen. So
electron.
you can't get an H2 plus because if it has 2 protons in its helium.
Mm.
Oh, I was thinking the other way.
So you cannot have H2 plus because then it's helium. Now, here's something interesting. So I take a medicine that controls the amount of acid that is produced in my stomach. And it is called a proton, if I can spell, pump inhibitor.
It's actually cadmium. Like, it's actually called that.
It's actually called that. It's called a PPI. I'm on a PPI. It's called a proton pump inhibitor. You have a pump in your stomach that churns out acid. The acid is just protons, and so it inhibits my proton pump.
Proton pump.
I love me some proton pie. That would be like lemon juice. Like,
Like lemon pie.
lemon pie. Actually, I do quite enjoy lemon pie. Yes.
Sometimes
Jeff.
good.
So, the acidity is just a measure of how many extra protons are in it.
How many extra protons, and basicity is a measure of how many extra OH minuses. They're called the hydroxide ion. Okay, so if it's acidic, there's extra protons. If it's basic, there's extra OHs, hydroxides. Yes,
What's more stable? Or can they, or they just?
they're both pretty equally stable. And actually, and like I said, so sometimes you'll have an H3O plus, and then the hydrogen breaks off, and then it comes back with the H3O, and it kind of comes
Wait.
in and out of this because this is not very stable.
Is that like when universal indicator, when you can put it in and it changes?
When it changes, we're gonna do this tomorrow, but you asked, so I'm gonna answer. So so this turned green, right?
Yeah.
I added a base to an acid. What happens if I have an H plus an OH minus? What am I gonna get?
Equal.
Nothing.
What are they gonna turn to?
Nothing.
It's good, you're gonna have a chemical reaction, absolutely.
Oh.
What is it gonna become?
Oxygen.
Oxygen?
H2O, guys.
I get smart.
So what happened was, so I had this acid, right? And I added the base, and it turned back to water, which is neutral.
Wait, so the green is water?
The green is neutral. There are other chemicals in here that are not water. Okay?
Wait, I have a question.
Yes, please.
If you were to add the base to that, would like the red still stay the same except get like a little bit more green?
We
still stay
could
at the
try it.
bottom?
I kind of want to keep this so you guys can all see it. We can try it. But today you're just gonna play with the concentration of acids. Tomorrow we'll play a little bit more with the properties of acids and bases. Costin and Sophie, you guys good? Do you have any questions?
No, I'm good.
Costin?
Should I?
Okay.
Let you guys.
He's making cinnamon
Yeah.
rolls.
He's off making cinnamon rolls.
He probably hears us talking about